Zurika Blanco. She's a young student of Cinvestav, and she's going to talk to you about two states of light in a non-linear Mach Zehnder.
Well, first I want to say thank you to the organizing committee for inviting me to participate in this conference series. For that, I'm going to present you is basically divided in three sections. In the first sections, I introduce you the nonlinear coherent states. In the second part, I mention some measurements of classicality, and in the last part, I will talk about interferometry. Here, let me begin with introducing the nonlinear coherent states. I have to say that this part of the work was developed in collaboration with Kevin, Oscar, and Sarah, and is already published here in this reference. And in this work, we are modifying the oscillator algebra, but introducing these ladder operators, and such that this operator, the action over the number Hilbert vector is given in function of this E function, which is a non-negative function. And we preserve the number operator of the conventional oscillator algebra. And this operator follows these algebraic relations given here. And remember, the number vector now can be expressed in terms of this ladder operator in this expression. I say that the E function is the only condition is that it has to be non-negative. Then we can choose it as a polynomial of L degrees, just like this. And after some calculations, we found that the En factorial is given like this. These polynomial oscillators are interesting because we can recover the conventional oscillator algebra, and also we can recover, for example, the U11 algebra if we choose these parameters and this expression, and the E function is now given like this. But if we solve this eigenvalue equation, we can show that this state is given in terms of as a linear combination of the eigenvector states like this, where this is a normalization constant given in this expression. And for example, if we choose the parameters for the ESU11 algebra, we found that this state receives the name of ESU11 coherent state. But we are interested in now if these states are classical or that is not classical. For this, we had a criterion of classical criterion to analyze the classicality of these states. That is the P representation. The P representations, if we found that it is as similar as the delta distribution, like the coherent states and the vacuum states do, this means that these states are classical. We can associate a classical analog to these states. But if this is following, that is the case of the number of states. This means that these states are non-classical states. When we calculate the P representation for the nonlinear coherent state, we found that it's asingular of the delta distribution. But here it is important to make a question: is this a sufficient condition to be sure that these states are we can associate a classical analog? And then for study more deeply these states, let us introduce the beam splitter. The beam splitter is an optical device in the laboratory with two inputs into two outputs, and is described by this unitary operator. And for example, if we get in the horizontal input the state one photon, and in the vertical the vacuum states at the output, we get this bed state, which is maximally entangled. And for example, if we calculate the density operator, we found that it has off-diagonal elements. That means that we have non-classical correlation in this output state. More generally, if we choose the number of states and photons, the output state of this splitter is given by this linear combination, and we can show that the density operator has diagonal elements, and therefore is no classical correlation present in the output state. These results inspired the paper published by Knight, where he said that if we want to have entanglement in the output of a mini splitter, it is necessary that one of both states in the input of the mini splitter has to be non-classical state. With this paper, we established something that we name Knight conjecture. And if we can verify that the output state has entangled, we can be sure that one of the both states that we are injecting is non-classical. For verifying that we have non-separable states of the output of the mini splitter, let me introduce the joint probability as a criterion. The joint probability is the probability of the m photons in the horizontal path or j photons in the vertical. If we found that this joint probability is factorizable, that means that the state of the output is separable. But if we found that the joint probability is non-factorizable, that means that the state of the output is non-separable. For example, let me retake the result of when we inject the number state in the horizontal input. We found this probability, this joint probability, which is this is the beta function, and we can separate this function into one that depends only of g and other that depend only of m. Therefore, we had that the joint probability is non-factorizable, then the state is non-separable. Using the Knight conjecture, we had that this state injector in this arm is non-classical, like we know for the number of states. Now let me introduce in the mini splitter classical signal, the Lugar coherent states. After the action of the unitary operator, the output state is given by this expression, which is a separable state. But let me analyze the joint probability to verify the criterion. We found that this joint probability is given like this, and we can factorize this probability in both. Then this probability is factorizable. That means that the state at output is separable, and using the Knight conjecture, that implies that this state is classical. We verified result. And here we plot the joint probability in terms of m and g. And here are some level curves of this probability. Now let me apply these two criterions to the two nonlinear coherent states. This, which is that is 2-1-1 coherent state, and this that is receives the Knight of natural coherent states. When I calculate the joint probability, we found that in both cases it's no factorizable. That means that the state of the output is non-separable, and using the Knight conjecture, then these states are non-classical states. And when we plot the joint probability, for example here in the level curve, we can see a squeeze in the line n equals g, and we think that this is associated with the non-classicality of the states. Moreover, we found a second order correlation function, and we found that these states are not coherent at the second order. Then we showed that these states are not fully coherent in the sense of Glauber. This is the reason that this state has no classical analog, even though the P representation is asingular of the delta distribution. Now, in this part, let me introduce a Mach Zehnder interferometer. A Mach Zehnder interferometer is a device used in the optical laboratory, which consists of two beam splitters and two mirrors, and sometimes here a phase shifter will vary the different path of the interferometer. But in this case, let us use a nonlinear medium described by this operator, and we consider a perfect Mach Zehnder interferometer. That means that the phase is equal to 0. This device is already known in the literature. It is the name of nonlinear Mach Zehnder interferometer, or also Dunningham renamed this as a quantum beam splitter. And Dunningham say that a quantum beam splitter is a device that can produce null states in the laboratory. Here, for example, if we inject m photons in the horizontal path and the vacuum in the vertical, at the output of this device, we found this state, which is a null state, is a maximally entangled state. And another result that we can find is if we inject the Glauber coherent states in the horizontal path, we recover this state that is an entangled coherent state. And it's important because using this device, we are producing entanglement using a classical state. We found that this state is already reported by Sanders in this reference. Now, we are interested in analyze the action of this nonlinear Mach Zehnder interferometer over a linear combination of the states. Note here that the state of minimum energy is the KS, and R can be finite or infinite. And this linear combination is important because choosing depending on Cn, we can recover, for example, Glauber coherent state or the nonlinear coherent state that we are studying. And when we inject this state in the nonlinear Mach Zehnder interferometer, the final state is given by this linear combination of null states. For example, if we choose the parameters Cn, R, and S such that we recover the Glauber coherent states, we verify the mentioned state is an entangled coherent state that we are mentioned. And now, if we choose these parameters to have the SU11 coherent state, or this to have the natural coherent states, at the output of this device, we had entangled nonlinear coherent states. And we can produce entanglement using it. Now, these examples are matched for when R is infinite. Now, what happened when when we had a finite linear combination? To measurement the entanglement of this state, we will use the entropy of entanglement that say that if we found that the entropy is equal to 0, the state is separable. And if the entropy is equal to 1, this means that we had a maximally entangled state. First, let us consider the vacuum state is in this linear combination, where after diagonalize all the density matrix, we found two G values different of 0, this, and the other G values are equal to 0. Then the entropy of entanglement is in terms of these two eigenvalues. And for example, if we choose the Cn such that we recover the optimized binomial quantum state reported in this reference, we plot here the entropy of entanglement for different value of R, and we can see that the entropy is more the state is more entangled when we consider more states in the linear combination. In the strings, here it means for p equal 1 means that we had at output the known state, and for p equal 0 means that we had only the vacuum state considered. Now, what happens if we remove the vacuum state in this linear combination? Well, after diagonalize the density matrix, we found only two eigenvalues, different of 0, and are this. And with this eigenvalue, we found that the entropy is equal to 1. The feeling is that these states are maximally entangled independently of the form of the end. And finally, I want to mention one more thing. This nonlinear Mach Zehnder interferometer is a proposal to improve the measurements in the laboratory. For example, when we use an interferometer with each state, with one state, at the output of this interferometer we had a choice noise limit. Let's see other limit that is the Heisenberg limit. This is the best of the best in the measurements, and in quantum metrology they propose to use if it exists a form to approach to the Heisenberg limit using exquisite light, but it's only approach. In the quantum metrology, say that if we use if we substitute the conventional beam splitter by this quantum beam splitter, it is possible to that the state at the output touch the Heisenberg limit, and this is a proposal to improve the measurements in the laboratories. And thank you.
Here we have Sarah. Maybe time for a couple of questions.
For your coherent state at the beginning, did you find another property like overcompleteness?
Yes.
Yes, they are overcomplete.
Yes.
Okay.
It followed all these properties of the coherent systems.
Okay.
Question? So I have one. These states which are now trivial states it is more feasible or susceptible of being measured in the laboratory to obtain this kind of state?
The nonlinear coherent state,
Yeah.
we hope that, but we don't know yet how to implement this in the laboratory, but it's an open question.
Okay, and that challenge is producing the input state or in have the arrange of the Mach Zehnder interferometer?
First, produce the nonlinear coherent states in the laboratory, and the alignment of all these objects is other problem, but
It's not conventional.
it's difficult, but it's possible
Okay.
to.
Okay. Another question?